So today, the big picture today, we're going to talk about something called the central limit theorem, which it sounds kind of scary, but it's actually really, really easy to apply. I'm not going to do the formal mathematical proof because that's like graduate level stuff. Now, the central limit theorem says, let's start off with the following. We have a normally distributed set of values. This is what we're starting off with. If I have a normally distributed set of values, I have no idea how much they're spread out. I just know that I got a perfect bell-shaped curve. If we had a normally distributed set of values, but the standard deviation was really small, then that set of values would look a lot more like this, wouldn't it? Okay? In other words, small standard deviation means small spread. If I had a set of values with a really, really large standard deviation, maybe they look like, like this. Okay? All of these are bell-shaped curves. All of these are normal distributions, but depending on the size of the standard deviation, right, that determines the spread. A large standard deviation means things are really spread out, which also makes it harder to be, a high or a low z-score. But that's okay. So, assuming that I have a normally distributed set of things, could be human heights, things of that nature, if I take an individual outcome, anything's fair game and I use my table, but what if I took an entire group of outcomes? I didn't say what's the probability that one individual is above or below or between these outcomes, but what if I said an entire group is above or below? Now think about that for a moment. If you went out, we want to find the average height of a Mesa College student. So you're going to go out and measure one person. Good idea? Why not?
Not enough data.
Well, first of all, what if that person's really tall or really short? I mean, what are the chances you're going to hit the average with one person? Probably not very good. But what if you went out and measured 100 people at random? Now, would it be so terrible if you had a really, really tall person in that group or a really, really short person? Would that really make a huge difference if you had 100 heights? Now you're talking, decimal place affecting, not big values. So clearly, the larger my sample, the more forgiveness there is if I do have outliers or extremes. Does that make sense? So if I said Mesa College students are distributed a certain way, but what if I said we're going to collect them 100 at a time? Oh, if I collect them 100 at a time, I would expect, my group could look like the blue, but if I collect large samples, the samples would look like the orange, in other words. The bigger the sample, the tighter and tighter and tighter. Now, it's never going to happen that your sample ends up being the entire population. You kind of missed the point. But if my sample was the entire population, it'd just be a line segment, right? There would be no spread because I have everybody. So the central limit theorem really says that samples tend the same way individual scores do, but they're much more tightly packed, which again means that I can make better conclusions with big samples. So I'm going to do a really simple example of something. Let's suppose we were measuring billionaires in California. And we want the number of children the billionaires have. Okay? So we discovered in California we had 5 billionaires. And the number of children they had was 0, 1, 4, 5, and let's say, just for fun, we have somebody who's crazy wild and they have, let's see, somebody has 10 kids. I'm just making up the numbers. Okay, so we have here's the billionaires in California. Now, if this is all the billionaires in California, is this a population or is this a sample? It's a population because I just said we have all of them. Okay, what is the mean of this population? And I would use mu. So how did you get that? You said 0 plus 1 plus 4 plus 5 plus 10 is 20, and there are 5. Yeah, exactly. Okay. Now, I want to go out and collect samples. Let's make it even better. Let's suppose I didn't know anything about the billionaires in California, but I'm going to go out and collect samples. So to make it easy, I'll just collect samples of size 2. I have 5 billionaires, and I'm going to go out and collect all of the samples that I can possibly do of size 2. Now, let's just say that Graham is one of the billionaires and Ava is one of the billionaires. You're in my sample. Does it matter what order I chose you? No, that's not a situation where it would matter. I'm going to pick you two, or I'm going to pick you two. I'm going to pick you two. So how many ways can I choose two of these 5 people? Would it be a permutation or combination?
Combination?
Why?
Because it doesn't matter.
What doesn't matter?
The order?
Order doesn't matter. Yeah, let's be absolutely certain. Okay, so how many different samples? How many samples of size 2? I'm doing a small problem purposely so you can see the outcomes easy. How many samples of size, we'll say little n equals 2. By the way, big N is 5. Remember, big N is the number in the population. I have a really small population. Okay? So how many samples of size 2? You just said combination 5 choose 2, which would be 10. So what I want to do is write down all the possible samples of size 2. Okay? So what would my possible samples be? I'll do them as order. I can have 0, 1. I can have 0, 4. I can have 0, 5. I can have 0 and 10. What else can I have? I can have 1 and 4. I can have 1 and 5. I can have 1 and 10. I can have 4 and 5. I can have 4 and 10. And finally, I can have 5 and 10. Everybody see that? Those would be my 10 possible samples of size 2, because you just said order didn't matter. So the order I write them, those. So my very first sample, I chose these 2 billionaires, the one with 0 kids and the one with 1 kid. Now, I want to find all of my sample means. How many sample means am I going to calculate? Obviously, 10. Now remember, when you do sampling because you do not know the population. I'm starting with a situation where I know the population, and I'm asking you guys to go out and collect samples. You don't know the population. So you grab the 0, 1, and Dylan, you grab the 5, 10. You're going to have very, very different answers, aren't you? So what we're going to do is, let's look at the 10 possible sample means. And sample means, we always use X bar. So let's make it easy. Let's call that the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. So I have X bar 1, X bar 2, X bar 3, X bar 4, X bar 5, X bar 6, X bar 7, X bar 8, X bar 9, and X bar 10. I think we could do these without a calculator, you think? So what's the first sample mean?
0.5.
Okay? And what's the second sample mean?
2.
The third sample mean?
2.5.
The fourth sample mean?
5.
Hopefully everybody sees what we're doing here. We're just averaging those 2 numbers. The fifth sample mean?
And 2.5.
2.5. The sixth sample mean, now we're up to 1.
3.
5. 3. The seventh?
5.5.
The eighth?
4.5.
Ninth?
7.
And the 10th.
7.5.
Now, first of all, my original numbers ranged from 0 to 10, and we said the mean was 4. These numbers have a smaller range, don't they? They have a little bit smaller range. They're a little bit tighter. My smallest is 0.5, my biggest is 7.5. That's the first thing you notice, that the sample means are less spread out than the individuals. If I had said consider all samples of size 3, this would have been narrower still, because the smallest would have been 0, 1, 4. That would have been the smallest mean, agreed? And that'd be 1 2/3. The biggest would have been 4, 5, and 10, and that's only 6 1/3. Oh, do you see what happens in that case? Every time I have a larger sample, the spread of the means would be smaller and smaller and smaller. I'd be tighter. That's the first thing you notice. Now finally, let's find the mean of all the sample means. And the mathematical notation we use for that. We use mu for the mean of the population. But I'm not averaging these 5 numbers anymore. I'm averaging these 10 sample means. So we write it like this. What is the mean of the sample means? So here's what you're going to do. You're going to take these 10 values, add them up, and let's divide by 10. Okay? So let's all do that with our calculators. You already have the answer? You are fast. So what is the answer you got?
4.
Oh, that's kind of weird. Why is that kind of weird? It's the same as the mean of the population. Well, this is the first absolute and one of the most important things of all in statistics. If I have a population, by the way, this is whether it's normally distributed or not. This is just always true. If I have a population and I have a population mean, whatever it is. Now, consider every conceivable sample of a particular size. This is important. Mesa College, we would have an average height of our students right now. Would you agree? Let's say today we were able to measure everybody. So in other words, some of you aren't going to grow an inch, in the next month. We were able to measure everybody and we found the mean of the population. Let's suppose we considered every sample of size, 100. And by the way, that would be really big because there's, 20,000 students. 20,000 choose 100 would be a number really, really big. But let's suppose we could actually take every conceivable sample of size 100, find the mean of the sample. Now, first of all, the mean of the sample probably isn't going to be too far off the population mean because it's a pretty big sample. But if I took every conceivable sample mean and then I took the mean of the sample means, it is absolutely equal to the mean of the population. The mean of the population equals the mean of all possible sample means, absolutely all the time. This is why, if you have a sample mean and your sample was pretty large, you have a lot of faith that your sample mean is really close to the actual mean. Now, would you say n equals 2 is a large size sample? It's a pretty small sample. No, so that's why these differ. But like I said a moment ago, if I said, now let's consider everything of size 3. I want to do that now too, just to show you how the spread changes. So everything of size 3, I'm going to have to write it up here because I can't see these numbers. Now there's 5, choose 3, which is still 10, by the way. So I'd have 0, 1, 4. I'd have 0, 1, 5. I'd have 0, 1, 0, 1, 10. My commas and my ones are starting to look right. Boom, 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 boom. Now I have 1, 4, 5. I have 1, 4, 10. Hold on, did I get them all? 0, 1, 4, 0, 1, 5, 0, 1, 10. Oh, sorry, I skipped one. I'm not to these guys yet. Now I'm at 0, 4, 5. 0, 4, 10. And then 0, 5, 10. There we go. Now, 1, 4, 5, 1, 4, 10. 5, 1, 4, 10, 1, 5, 10, and finally 4, 5, 10. There we go. Those are the 10 possible samples of size 3. Let's do exactly the same thing we did a moment ago. Let's find the 10 sample means of these guys. Yeah, you would never actually go to all this much trouble, but I'm trying to illustrate a point with our results. So let's take the average of each of these 10 samples. So 0 plus 1 plus 4 divided by 3. That's 5/3, right? If I do that as a decimal, that'd be 1.6 with a bar on it. 5/3 would actually be easier in calculation though, right? Because I'm going to do these on my calculator in a moment. What's the next one? 0 plus 1 plus 5 over 3 would be 2. The next one, 0 plus 1 plus 10 would be 11/3. That's 3 2/3. The next one, 0, 4, and 5 divided by 3, that's just 3. 0, 4, here we go. 0, 4, and 10, that's 14 divided by 3, that's 4 2/3. 0, 5, and 10 divided by 3, that's 5. 1, 4, and 5 divided by 3, that's 3 1/3. Over here, 1, 4, and 10 divided by 3, that's just 5. 1, 5, and 10 divided by 3, that's 16/3, so that's 5 1/3. And then finally, 4, 5, and 10, that's 19/3, so that's 6 1/3. So the first thing you notice, the spread. My original spread went from 0 to 10. When I had samples of size 2, my spread went from 0.5 to 7.5. Now that I have samples of size 3, what's the spread? 1 2/3 to 6 1/3. That's narrower still, isn't it? Do you see that my spread is getting narrower and narrower and narrower as the sample gets bigger? Now, let's add all of these up and divide by 10. We already know what the answer is going to be. It's going to be 4 again. Because we just considered every sample of a particular size. Do you notice I don't take these samples and combine them with these samples? That's not how it works. It's every sample of a particular size. If I take all of the sample means, they always give me the same as the population mean. Now, in reality, would you take multiple samples of different sizes? No, you just take one sample, but you have faith that if I take a large sample, the scores are lesser and lesser and lesser spread out. Now, the other thing is, if the scores are less spread, then the standard deviation is less spread, isn't it? If I took a really wide range of values, let's take SATs. We've been dealing with that lately. All right, I know the standard deviation is 100 and the mean is 500. And that's a pretty big range, right? 200 to 800, you know, that kind of thing. What if I took 100 people or 1,000 people? Those scores would be so much more narrow. Now, the average would still be 500, but the standard deviation would be so much smaller because I'm taking a huge sample. And I'm saying, what about all the people if I took large samples? They would be spread so much less. So there's two huge results from the central limit theorem. This, okay, in general, this is true. If I take all samples of a particular size, find every conceivable sample mean, and then average the sample means, nobody would do this because that would take forever, it would equal the mean of the population. But what about the variance of the sample means? That's what we really care about. I just demonstrated this rather easily with 2 examples here. That's pretty simple to understand. But we expect the variance to be less because the larger the sample, the less spread we see. That was what I was illustrating with my curves. Turns out this is equal to the actual population variance divided by the sample size. So the larger the sample, the less the spread of my sample means. Now let's go back, say again. Mesa College students, let's use inches because it's probably easier to conceive. So the shortest person on campus, let's assume we don't have any dwarves. I mean, maybe, I don't think we do, I'm serious. Right? The shortest person on campus is probably maybe 4.5 feet tall. If we just had to make a guess, probably, and so in the low 50s in inches. And the tallest person on campus, what do you think tallest person on campus is? Probably in the 80-inch range. Right, close. I don't know if we have any 7-footers. 80-inch would be 6'8". So we'd have a range of heights maybe from low 50s to about 80. And maybe the campus mean is around 65 inches. But if I said, let's take a sample of size 100 and find the mean of that sample, well, we'd expect the mean of that sample to be not too far off the overall mean. And then you took a sample of size 100, you took a sample of size 100, you took a sample, all of us took samples of size 100. What we would see is our samples are not very spread out. The individuals on campus are very spread out, but our sample means are not very spread because they all should be relatively close to the actual mean. Does that make sense? So we said, well, let's consider all of our sample means. Then if we took the variance of all of our sample means, what we'd see is it's really small because we take the population variance simply and divide it. So if I said consider samples of size 100, then the variance of our sample means should literally be the population variance divided by 100. That makes it really small. That's why I said the curve looks like that when the sample is large. So if that's the variance, then what would the standard deviation be? Well, it would be the square root of this, which is simply that over root n. And that's kind of the magic number that we use in calculation. Because when you're doing your calculations for z values, you use the standard deviation, not the variance, correct? So I'm going to give you, we're going to do some really simple examples, but this is actually the way of things. Because it is not reasonable to try to make conclusions about populations with samples of size 1. Does that make sense? I'm going to take a sample of size 1 and use that to make my conclusion about planet Earth. That probably would be dangerous. Do you agree? I'm going to take a water sample, a small water sample, somewhere in San Diego, and just take one small sample. to determine all of the water quality in San Diego County. Wow. Wouldn't it be better if I took lots of samples all over the county and looked at all of them? Wouldn't that be a little bit better? Because what if my sample was from the most pure spring water humanly possible? And say San Diego has the most perfect water on earth. Or what if my sample was from the Tijuana River? You know, my sample caught fire before I actually measured it. That's not a joke. You know, I say the worst, most polluted water on planet Earth. Well, you can't measure anything about a population by taking a sample of size 1. That doesn't work. Some of you, how many of you look at Yelp? Most people say like for restaurants and things like that. A lot of you will look at a Yelp review. Or maybe you're going to hire a mechanic or something and you don't know anything. So you look at a Yelp review. And maybe you saw really good numbers or maybe you saw really lousy numbers. Does any of you ever look at how many reviews there are? You saw a really good review and there was only, you know, 1 person or 2 people. We had an instructor who's no longer here years ago who had not a very good reputation. They were one of these people that they only taught at night, so no one ever saw what they did, and they never get through any material, ever. They wouldn't even come close. When I would sub their classes, I would do a lecture, and I'd literally cover 3 lectures at once, because if they got halfway through the material, they were doing fine. And I had a former student who, because of scheduling, had to take this instructor for the next calculus class. And they did the unthinkable. They did the whole rate my professor thing, not realizing that that's a voluntary sample that is extremely skewed. And they saw the person had a great rating. So they took that instructor. They realized later there had only been 1 person who had filled out the rating. And it was the worst, they said it was the worst nightmare of their life. This was a student who was 100% in my class like every semester. And they ended up dropping that class because they were failing it, because they weren't getting any instruction whatsoever. And they said, well, but the ratings were so high. And I just laughed. I said, yeah, if there's 10,000 ratings, that might be meaningful, but there was 1. Again, that's like asking a perfect stranger, what'd you think about the movie? And they said, oh, I loved it. That must mean it's a great movie because 1 person said they loved it. What if the next person said, I hated it? Oh, that must mean it's a terrible movie because 1 person said they hated it. Would any of you trust a sample of size 1 to make a really important decision in your life? I hope not. No, you would say, I would like a large sample and look at the sample results. Now, I'm using Yelp reviews as an example because I know people with businesses and it only takes 1 bad review to really mess things up. But a bad review when you have a lot of good reviews is going to have a much less effect, isn't it? Again, it's like saying we're going to take the sample of size 100 to find out the average population of a Mesa, or the average of a Mesa College student, and you happen to grab the tallest person on campus in your sample. You have no control over that. Right? There has to be a sample out there somewhere that has the tallest person, right? But if you had a large sample, is that going to have a huge effect on your sample mean? Not if it's a large sample, because again, large denominator, much less impact. So that's the idea. So the central limit theorem says that sample means, and here's the crazy part. If I have a population and the population itself is not normally distributed, the sample means still are if the n is large. So I could have a skewed population like income. But if I grab large samples and look at all the sample means will basically look normal, even if the population is not. And that's how we can make really more powerful conclusions. So that's, the question was, you know, I think you asked this question last day, can we always use the z-table to do this? Not on individuals, no. But on large populations, we can, and have a lot more faith. There's actually another way we do it if it's not normal, but that normal distribution works really well on a large population. So, let's go back and look at, how about SATs? All right, so SATs, we know the mean is 500 and the standard deviation is 100. We know this. This is not mystery material. So after a particular SAT, you grabbed an individual at random, however you wanted to select it. Maybe it's at the high school you're working at, or maybe it's just, you just grab somebody walking out the door, you say, what is the probability that an individual had a score, let's keep it simple, had a score greater than 550? Okay, well, I need to convert this to a z-score. Agreed? So how do I do that? 550 minus 500 over 100. Okay? You guys all have your Z tables on you, I hope? 550 minus 500 over 100, that's 0.5 exactly. Since it's a greater than, what do I need to do? 1 minus. Okay, and what do we get? Find that number for me. What is the probability? So what probability am I subtracting there?
0.6915.
6915. So the answer would be 3085. So if I grabbed an individual at random, the probability that their z-score exceeds 550 would be a little more than 0.3. Okay, great. Now, I'm not going to grab an individual at random. I'm going to grab an entire sample of people. Okay, so different question. You have a sample of size, let's say n equals 15. I have a group of 15 people at random. I randomly chose 15 people. Find the probability that x bar is greater than 550. The group sample mean, in other words. An individual has about a 0.3 probability of being greater than 550, but I'm grabbing a whole group of people at random. Do you think that's going to be easier or harder to have that high of a SAT as an entire group? Probably harder. It'd be sort of like saying, I'm randomly going to select an individual, you know, the probability is not going to be very high that they make $1 million a year. Now I'm going to grab an entire huge group of people. What's the probability the entire average of the group is over $1 million? Probably darn near impossible, right? Not for the entire group. An individual is one thing, an entire group, wow. So how do I do this? It's going to look almost the same as that problem, except we are going to do that. So now the question is, what's the probability that x bar is greater than 550? This is not the same as this. This is an individual outcome. This is an entire sample. So what's different about this? This will be the probability that z is bigger than 550 minus 500, just like before, over 100 over the square root of 15. So from now on, this is pretty much the way we calculate the z-score. Because you're not going to be dealing with individuals in general, you're going to be dealing with entire samples. That makes a lot more sense. And again, I want you to think logically. I gave you the tire example at the beginning of class. I'm trying to figure out, how long tires last. Particular company, perhaps. You don't take one set of tires and measure them. You take a whole bunch of set of tires and find the average. It makes a heck of a lot more sense that way. Because what if the one set of tires you chose was an outlier? Are you going to make a good conclusion in the end? Again, that's like saying, I want to find the average height of a Mesa College student by randomly selecting one person. That's not a very good way to go because that person could be an outlier. But if an entire sample has an outlier, that's a lot less. Okay, so let's calculate that z-value. And what does this come out to be? I don't have a calculator. So what does this come out to be? Probably want to use your parentheses. Parentheses in the numerator, parentheses in the denominator. The z-value should be much bigger. Should be bigger.
I got 1.93.
Yeah, I think you the wrong way on your root 15. When you divided the 100 by root 15, your standard deviation was now much, much smaller, which means your quotient should be much, much bigger. So you got about what, 1 point?
1.94.
That sounds about right. Anybody else you got confirmation? Now, this is 1 minus the probability that z is less than 194, which is 1 minus what? The z value 1.94, the probability of being less than that is, anybody? Table?
973.973.
9738, but we're doing 1 minus. This is a very interesting result, folks. I'm grabbing, and this, by the way, this is absolute what I'm showing. This isn't a made up situation. You're going to grab an individual at random who just took the SAT. What is the probability that person scored above 550? About 0.3. You're going to randomly select 15 people. What is the probability their group average is above 550? That's a lot harder, because that means that really, it's like saying all of them had to be really good, didn't they? Oh, if the probability an individual is good is one thing, the probability an entire group is really good should be a much smaller number. That's a much smaller number. That's way smaller. That's what the power of a sample does. It makes the spread smaller, so it makes your conclusions a little bit better. This is, by the way, we're going to be doing a lot of this later when we get to what's called hypothesis testing. But when we're trying to compare, I'll give you a simple one. Let's just say we were trying to compare the quality of students at Mesa College versus some other college. How would we do that? Well, let's grab our smartest person and compare it to their smartest person. That probably wouldn't work. Wouldn't we want to take like our average versus their average? But how would I do that? Select many Mesa College students and measure them in some capacity. Could be a test, I don't know. Take a bunch of their students and measure it in some capacity and then compare the averages. Wouldn't that make more sense? Not compare 1 versus 1. Does that make some sense to you? In reality, again, samples of size 1 are very dangerous. So now, sort of the new way. The probability that x is, just in general, let's say, smaller than a value. We know this is equal to the probability that z is smaller than value minus mean over standard deviation. We know that. That's what we've been doing. So what's the difference? Now I'm saying the probability an entire group average is less than that same value. Entire group average. Please never confuse x with x bar. They are not the same thing. An individual value and an entire mean of a sample are not the same thing. In fact, they're never going to be the same thing. What's this? Well, everything looks exactly the same. But what's my denominator now?
Square root of 18.
Sigma over root n. Oh. Now, what some people do, and I think this is overkill, what a lot of folks will do is say, since this is actually the formula we're going to be using from now on, what if I'm looking at an individual value? What's n for an individual?
Small n.
No, what's n? 1, yeah. If you only have one person, it's 1. Would this formula still apply if I only have a sample of size 1?
Yeah.
Yeah, I just think it's redundant to write sigma over 1. It's not incorrect, by the way. But I think writing over square root of 1 and then doing the calculation, that just makes it kind of muddled. Sample of size 1, sample of size n. Got it? So a sample of size n, you're not looking at an individual outcome, you're looking at an entire group of outcomes. Okay? Now, something that I've been paying a lot of attention to lately are housing prices and interest rates. How many here rent? Renting has gotten just completely insane. In fact, I know people that rent and they have a significantly smaller home than I live in, and their rent payments are significantly larger than my mortgage payment. It feels very wrong. But now with the houses selling, May, June, in my neighborhood, if you put a house up for a fair price, it was going to sell within a day or two for significantly more money than you asked, if you asked a fair price to begin with. People would bid. Now, you can't give away anything because the interest rates have gone so high that same house is now dropping in value because people can't get the mortgage. So it's a horrible situation. You can't buy a house right now because the interest rates are so ridiculous and the prices had gone up. But renting is almost worse. So it's a very difficult situation. So here's the question. We're looking at a particular area. And by the way, we know that housing costs in general, like income, are skewed to the right. But what is different is housing prices in particular areas, particular regions, are usually somewhat normally distributed. I live on a cul-de-sac, so there's not a ton of houses on my street. I don't know, if I had to guess, I'd say maybe 30 houses. I don't know, I could be wrong. But in that neighborhood, you're not going to have a shack that's not worth anything and a super bazillion-dollar mansion on the same street. In fact, most people realize when you go to buy or sell real estate, your house is worth a certain amount, but you know what determines the value of your house more than anything else? Yeah, exactly, your neighbors, right? What is, it sounds ridiculous, but I've known a few realtors, they always say the three most important words are, you ever heard this one? Location, location, location. You ever heard that corny statement? In other words, the only thing that matters is not even your house, it's where your house physically exists. You could have the nicest house in the world, but if you're in a lousy neighborhood, you're not going to get as much. If you have a lousy house, but you're in an incredible neighborhood, you're going to get a lot more. So the point being, small regions, neighborhoods, those houses are going to be pretty much normally distributed because you can't be too far away because the neighborhood really determines the value. So if we said in a particular area, okay, in a particular area, let's keep it simple. I mean, that particular area could be, La Jolla. That particular area could be El Cajon. But in a particular area, we're not talking about all of San Diego County. We're not talking about the United States. In a particular area, let's say the average, or I'm going to say the mean, home price is, we'll make up a number, say $651,800. Okay. With the standard deviation of, how about, $52,600. These are pretty reasonable numbers. In a particular area, the mean housing cost of all of the houses in that area. We're talking about a particular area. Are we talking, is this a sample or a population? It's a population because we're considering all of the houses in this area. Not in the United States. No, but that might be 1,000 houses. It might be 10,000 houses. It might be 100 houses. But we're considering all the houses in a particular area. And we're saying essentially the values are normally distributed with this mean and this standard deviation. So if I said you're going to grab a house at random, what's the probability that it's a certain price range? Or you could just simply say, well, how many of these houses, what percentage of the houses are above a certain amount? That's an easy way to say it. So in this particular area, you want this region. You want to live in this area. You really like this area. You like everything about it. You like the schools, you like where it is, but maybe this is outside your budget. Okay? Maybe you got approved for loan, but maybe not quite that much. So, you're looking for an individual house. So I want to find the probability, I'll say it in words. A house sells for less than $600,000. Because that's really your range. Now, when you're looking at those values, look at my standard deviation. Would you say that's about one standard deviation below the mean? Mm-hmm. So you're really asking, what's the probability of being roughly a standard deviation below the mean? That's not a hard question. So I'm asking you, what's the probability an individual house sells for less than $600,000? Now, I can't look up $600,000 in a table. I have to convert this to a z-score, obviously. So it's the probability that z is less than 600,000 minus 651,800 divided by 52,600. This is one house. If you want to write over the square root of 1, that's okay. I just think it's overkill. Okay? Let's calculate this. So first of all, what is my z value that I'm looking for? I'm going this way, aren't I? This is what we're looking at because we're below average right now.
Negative 0.98.
Okay, so the probability that z, does everyone agree with that? Negative 0.98?
Yeah.
Okay, remember, correctly rounding. Now, let's look up that value. I don't have to do anything with it because I'm asking a less than. So negative 0.98. Hold on, we're all looking at the same thing.
No,
98?
1635.
I think you're on the wrong line. 1635?
1.1635.
Double check me, do you get 1635?
Oh, yeah.
Okay, make sure we're all looking at the table. So in words, I want to move to this area. I am looking for houses in a particular price range. Roughly what percentage of the houses in this area can I afford? Around 16% of the houses. Does that make sense to you? Okay, I really like this to make real life sense. We're saying in a particular area, these are the numbers, and it's essentially normally distributed. Is it a perfect normal distribution? No, but it's essentially normal. So for all practical purposes, I can use the tables. So I have a price range. I have what I can afford. And by the way, this is actually how it works in real life. You want to buy a house, you've been saving up, you've got a good job, all of these things are cool. You don't get to determine the price of the house, sorry. Who determines the price of the house you get to buy? The bank. The bank. Because you have to get pre-approved for the loan, and they will tell you based on all of these factors, on your income, on your credit, and on your savings, how much you can put down. Here is the maximum you can get, because in other words, you have to borrow the money. Nobody buys I just happen to have $1 million in my pocket, I'm going to buy a house. That's not how it works. You qualify for the loan and all that kind of stuff. So in this example, you've qualified for a loan to be able to buy a $600,000 house. That's the way it is. Now here's the interesting thing, because I pay attention to this stuff. In May and June, interest rates were still under 3% for mortgages. So houses were selling like hotcakes. A house in my area had just been fixed up. The old folks had moved out. They fixed it up, did a lot of nice stuff. It's not a huge house, but they did a really good job. But they way overpriced it. I mean, absurdly overpriced it. And we're all doing, the walk-ins on the open house because we wanted to see what they did. Like, I love what you did, but you're way overpriced. And the realtor said, oh no, this house is going to sell within a week, probably for, way more than we're asking. That was in June. That house is still sitting empty on my street, and they've lowered the price multiple times, and the house is never going to sell. Why? Because interest rates were under 3, now they're over 6. What does that mean? That means the person that could have qualified for that mortgage in June cannot qualify for it anymore because the interest rates are so high, that means your monthly payments are so high. Now that same person is qualifying for a house that is significantly less. That's how it works in real life. So you've qualified for a $600,000 house. About how many of the houses in the area, therefore, could you afford? Around 16% of them. That's why I'm showing you an example like this. Now, you want to say, well, I'm considering maybe an entire street in that area. Not one house. I'd like to know, in general, how about if I took a cluster of houses? So this was an individual house. Now I want to find out an entire group. Maybe I have a lot of relatives, and they all want to buy in this area. Have some fun with that. I got a big family, and everybody wants to buy a house. As silly as that sounds, I know families who have actually multiple houses in a row, and some at the end of my street. So now let's say, same question, find the probability of a house sells less than 600. Let's find the probability that, let's say, 10 houses, cumulative, sell for less than 600,000. So I have any group of 10 houses, their average will be less than 600,000. That's what I'm saying now. I have a group of 10 houses. Not every one of them is under 600,000, but as an average, they're less than 600,000. And that might sound silly to go, why would you think of it that way? I have a young friend who works for Apple up in Cupertino. Apple, that's literally, like, it looks like a spaceship. Has anybody ever seen that? I mean, they have thousands of employees. They have restaurants, they have gyms, it's interesting, he says they created an environment where they actually don't want people to leave. They want you to stay when you're not working. But what did they do? They bought up all of the land in a very large area. I understand that, I could get this wrong, is it Google? One of the big companies is doing that right now in San Diego County. They want to build one of these gigantic clusters. And what are they doing? They're buying up a lot of land, and they literally want to develop a few thousand houses so that the employees can live there. Now think about this logically. That would be so unbelievably expensive. But if they decide to make the houses in a particular price range, they have total control because they own all the land and they own everything else. So this is what we're talking about. There's a bunch of people that work for a company on the East Coast and they all want to move to this neighborhood and they all have a similar price range. What's the probability that an entire cluster of 10 houses, any group of 10 houses, has an average of less than 600,000? Again, is the probability going to go up or going to go down, you think? So it's going to go down because I'm saying a whole group of houses have to be cheap. So what's the difference in this? We do the same thing. The probability, this time it's X bar is less than 600,000, is equal to the probability that Z is less than 600,000 minus 651,800 over, everything looks exactly the same, except I have a dead 10. That won't work. Except there's a root 10 now. One of the things, if you think about it mathematically, makes it easier. Whatever you got here, you're actually going to multiply this by root 10. Because the root 10 is in the denominator of the denominator. So it literally would come to the top in that case. So this changes things dramatically. What's the probability that Z is less than negative 0. Or is,
I got negative.
not 0 point, sorry. Negative, probably large, what is it?
3.11, negative 3.11.
Do we have confirmation on that? You got the same thing? Okay. Probability of Z is less than negative 3.11. Let's find that on the table. We've got a number? What is it?
1.0009.
Whoa! How did that happen? Because what's true for an individual is not true for an entire group. Remember, entire groups are much less spread out. So that means you're asking more than 3 standard deviations. An entire group of houses having this average is more than 3 standard deviations away from the mean. Yikes! Does that surprise you that how low that number is? Yeah, you wouldn't have seen that coming necessarily. So the idea is, if we said, what's the probability of an individual outcome? We know exactly how to do it. That was the entire last lecture. Now it's what's the probability of an entire sample? Everything's exactly the same, except we now have to account for the size of the sample.
So this is saying that the houses are right next to each other, right?
This would be like, not necessarily, but saying any cluster of 10 houses, it could be right next to each other. But
Like-
since it's random,
But so it's not like 10, one over here, one
but
over there, one over there.
depending how you wanted to word the question, it could be that, it could be all 10 are together.
I'm just wondering, I'm having trouble understanding why it wouldn't be still 60%.
They wouldn't need to, okay, well, it's sort of like this. If the probability that you're going to flip a heads is 1/2, then the probability that no, that would probably not be as good a one. If the probability I flip a head is 1/2, then what's the probability of flip 10 heads in a row? Well, it's still 1/2. Well, no, it isn't.
Oh, okay.
The probability of one thing happening was this. The probability of that thing happening over and over and over and over again can't really be the same thing. Now, I'm not multiplying probabilities in this case, I'm actually looking at the areas under the curve. But does it make sense why it can't be exactly the same? Because I'm asking multiple occurrences. The question is, does these houses have to be in a row? No, remember, I have people on the East Coast are moving here, and they're moving to this small area. And each of them has a need. What's the probability the whole group average is less than? They don't necessarily have to be, but any group of 10 houses that I choose, they could be next to each other, they could be extreme, because all of those would be included in groups of 10.
Right.
And I'm saying, wow, it's very unlikely now that a group average, okay? Again, group averages are much more narrow, and that's a good thing when I'm making conclusions. I'll go back to tires. You have a set of tires, they lasted an absurdly long time because of the way you drive, or you have a set of tires, they wear out really fast because of maybe the way you drive or the type of car. Is that a thumbs up or a thumbs down on that tire company based what you got out of them? Yeah, because I just gave you examples. You might be a person, I mean, you literally, you never go more than 20 miles per hour, no matter where you are, right? And you never hit your brakes, you slow down to stops. Braking wears out tires. You drive silly. You're a person who you take every corner too fast, and you do everything wrong. That's not a good indication. But what if we said, we're going to grab 100 people at random and look at how long their tires lasted as a group? Now if that number's low, is that more of a condemnation on those tires? If the group average was actually really high, would that be a thumbs up on those tires quality? Yes, not one. But if I have an entire group looking good, you'd say, I trust that outcome a lot more because the probability of the group having really good numbers or really bad numbers is much smaller than the probability of the individual. Does that make sense again? Again, if the probability of an outcome, and I took an extremely good outcome, the probability of being that good or better, we'd say it's probably small. But now if I take the entire cluster being that good, that's really microscopic because you're saying a random sample, and I just happened in my random sample, got all the tallest people on campus, or the oldest people on campus, or the smartest people on campus. My entire sample, you'd say, that's pretty unlikely. That's another way of thinking about it. So, let's go back. Now let's look at the IQs, okay? The reason I like using this one is just basically the numbers are so friendly. It's just really easy to do the calculations because I don't have icky decimal values. Again, like SATs, these numbers are standardized. So if the average human being has an IQ of 100 with a standard deviation of 15, then probability and individual is between, let's say, 97 and 106. Let's find that probability. What is the probability an individual is between, again, a randomly selected individual? It could be somebody in this group, okay? So the question is, what is the probability that X is between, and X is, because X is my outcome, X isn't my z-score, X isn't what I'm looking up, I gotta calculate that part. So this would be the probability that Z is between 97 minus 100 over 15 and 106 minus 100 over 15. So the only calculation truly in this problem is just simply reducing those quotients into a 2 decimal place value. Why 2? Why not 3 or 4? Why do we do 2 every time for the z-scores? It's not that it's more right than something else. What do your tables have? They're all 2 decimal places. So giving more decimals is fine, but it doesn't help you look it up. But giving too few decimals is ambiguous, because there's always going to be 10 probabilities for a 1 decimal place z-score. I need 2 decimal places so I can look up the exact. In reality, you can give as many decimals as you want. But I need 2 to look it up in the table. So, what are my 2 z values?
Negative 0.26.
Negative 0.2.
Yeah, I think 0.2. I think you hit,
Ooh, shit.
oh, you did 96.
Oh, is that what it is?
Yeah. So it's 3/15, so it should be exactly 2, and what's the second one?
0.4.
0.4?
Oh, you're right.
Now, I'm doing a betweener, so what do? The probability that I am smaller than the bigger one minus the probability that I am smaller than the smaller one. They have to be less thans. I can't look up greater thans, I can only look up less thans. So again, what you just did, you said I want the area between, so I take the bigger one minus the smaller one, and that always gives us the between. That's why they both have to be less thans, and I gotta take the bigger minus the smaller. Some of you last day were showing me, I'm doing everything right, and I keep getting negative answers. What is the only way you can get a negative answer? Yeah, subtract in the wrong order. You want smaller minus bigger. And is that an easy fix? Yeah, just switch them. It's got to be the bigger minus the smaller, otherwise I'm going to get a negative area. And there's two outcomes you cannot have. You can't have a negative, and you can't have one exceed 1. How would I ever exceed 1? How could I ever exceed 1? Because I added them inadvertently. I just simply hit the wrong button on my calculator. I wrote it down correctly, hit the wrong button, got a number bigger than 1. Again, the red lights should be flashing at that point, right? You're using DEFCON 4. Can't be negative, can't exceed 1. Probability is between 0 and 1. All right, what are these two values?
Oh, 0.6554 minus 0.0228.
Does everybody agree with that?
Yes.
0, 2, hold on. That's not right.
No?
Yeah, that's too small.
0.4207.
I think you looked up -2, not -0.2.
Oh, yeah.
So what's the second one?
1.2.
You still understand?
0.4207.
4207? Okay. You know how I knew that? Because this is not that small, right? This is just a little less than 0. So I would expect the probability to be a little less than 0.5. But the number you gave was so small, I go, no, it's probably -2.
Yeah.
Now, what is this answer?
0.2347.
Okay, so almost a fourth of human beings are going to be in this range. Great. Now, I want to grab a sample. I want to grab a fairly large group. How big is large? Well, more than one, obviously. I want to grab a group of individuals and say, what's the probability an entire group of individuals have this? Now remember, groups are much less distributed. Individuals have a standard deviation of 15. Groups have a standard deviation of 15 divided by the square root of n. In other words, the square root of the sample size. That's an absolute. That's called the central limit theorem. That's considered the most important concept in all of statistics. The question I get asked a lot by people who, especially who don't have statistics, is they've heard things about stats and go, how can you make conclusions about stats, or using stats? The most common one, near an election, right? We've used this example before. We'll use it again later. Opinion polls. Everybody's heard about opinion polls. And every time you watch the news, you'll see opinion polls. And you say, how can I possibly trust that? They didn't ask me. Has anyone ever had that thought before? How can they possibly say that? They didn't ask me. You know, how could they say this is the nation's opinion? Well, because they did the sampling correct. And they're saying, based on our sample, we believe we nailed it. Now, could it be off a little bit? Sure. That's why they always say this sample comes with an error of plus or minus, usually it's 3%. Oh, why? Because they didn't ask everybody. There's some wiggle room there, and that's actually correct mathematics. When you take samples, you didn't take everything. But the larger your sample, the closer your sample mean is going to be to the actual mean. Because they're less and less and less spread out. The larger the sample, the curve is looking like that. There's my bell-shaped curve. Big sample, there's my bell-shaped curve. That's why I can trust outcomes with big samples. It's actually that simple. And we're going to see as the mathematics goes. That's why the central limit is so powerful. Central limit theorem. Because the bigger my sample, the less spread. Therefore, extremes become far less likely. Entire groups having extreme averages is very unlikely. So now I want to do the same question, but you're going to have n is going to be, let's say, let's make it simple. N is now 16. I've randomly selected 16 people from anywhere. What is the probability that group of 16 people has an average, or has the average IQ, I should say, of the group is between 97 and 106. So now the question is, what is the probability that an entire group of 16 is in this range? Well, everything I just did looked almost the same. What's different? What's different? Over root 16, over root 16. Root 16 is exactly 4. So I'm lazy. That means that each of these is going to be exactly 4 times bigger. Because of where the root 16 lives. It lives in the denominator of the denominator. Oh, okay. So what is that going to do for my z-scores? So when you do that calculation, now what are you going to get? Negative 0.8. And what's the other one going to be? 1.6. Hopefully you get something that looks like that. Y'all get that? So therefore, my answer is going to be the probability that z is less than 1.6 minus the probability that z is less than negative 0.8. Now that is not going to be the same probability. Remember, when I have samples, they're less spread. I'm going to give you an illustration that might help you understand what we just said. So what are the numbers, by the way?
0.9452, 0.7881, 0.7881.
Well, it should be less than 0.5. I think you looked at
0.2119,
2,
119.
119. Yeah, that makes more sense. And so what does that give us? Wow, that's way bigger. An individual being in this range, less than a fourth of the people are in, almost a fourth of the people are in this range. But if I took groups of 16, almost 3/4 would be in this range. I'm going to give you a picture that will help you make sense of what we just did. Here's what we just did. Here's IQ. And I asked you between 97 and 106. I said probably like, Okay, that's what we just did. Now, I have a sample of size 16. I have a sample of size 16. Before, the area was under the black, but now there's way more area because this curve is much less. In other words, how much am I excluding now? A lot less. In fact, this curve probably could have made it much more narrow. In fact, it might even be more like, the larger the sample, the taller and more narrow the curve is, but the mean is still the same. Okay, the mean of the sample means is never going to change. If you consider every sample of size 16 of all the people in the world, that would take us like 1,000,000 years to do that. And it's still going to be 100 is going to be the average. But the spread is going to be only 1/4 as much. Why? Because I'm dividing by square root of 16. Oh, so if I take a really large sample and I'm dividing by the square root of that number, that's going to make my spread almost non-existent. That is the whole point of sampling. When you sample correctly, you can really reduce the spread. Now, in real terms, I want to talk about the tires, you know, and I want to really have a good idea of the tires. So I'm gonna test 10,000 sets of tires. There's nothing wrong with that concept. I'm gonna get it right. But how much is it? How much did you pay for your set of tires?
400, I think.
Oh, that's cheap. I just paid like
I
$6.
went back to the dealer and he hooked me up, but yeah.
Oh, okay. I just bought tires a couple months ago, about $650. 10,000 sets of tires. That's many, many millions of dollars, isn't it? Many millions of dollars that I'm basically throwing away. So, yes, I want to get really accurate results, but can I afford to test 10,000 sets of tires? Okay, one of my favorite ones, we did this in grad school at San Diego State. I want to test the brakes on a car. Now this is tricky, because wouldn't you want to know that the car you drive, the brakes are really good and really safe and really effective and going to last a really long time? Yeah, you have to change the brake pads and the rotors periodically. You know, my car is a 2007. I've had to do it once. You know, changing, that's normal wear and tear, but you would want to know that your brakes are good. How do you test brakes on a car? It's only one way.
Crash it.
It's called crash test. You guys have seen the illustration. In fact, who's sitting in the car? They are called crash test dummies. Yeah. You've all seen and heard that. You cannot test the brakes on a car without actually crashing the car. There's no other way. So we've just come out with the new Lamborghinis, and we want to make sure they have the best brakes on planet Earth. So we need to, do some crash tests on our Lamborghinis. So we'll maybe grab like 100 of them. You think? Again, problem is I can't afford to do that. I mean, there probably aren't 100 on planet Earth, by the way. I can't crash test all of the cars to determine if the brakes work, so I got to figure out a different way of doing this. You can't always have large samples. Remember I said when it came to sampling, there was only 2 factors that you always have to consider? Do you remember what they were? Up there. Time and money. That's always it, whatever it is. I need to crash test cars. That's a money thing. That's not a time thing. I need to test the tires. It's a money thing. So you have to choose samples that are large enough that you can be satisfied with your results, but not so large that you're going broke. You know what I'm saying? Now, I want to measure people on Mesa campus's height. Is there any money involved in that? No, it's only time, isn't it? I want an opinion poll. The election's next week. I want to find out what people are thinking. So I want to really get this right. I'm going to ask thousands of people and take about 3 months to do my sample. The election's next week. Is that going to work? Probably, yeah. I don't really want to do the opinion poll after the election. So now your time is your thing. Whenever you hear about an opinion poll, it's usually, there's several types of opinion polls. There's opinion polls just kind of like a running, what are people thinking? You're the most common one you'll hear about are things like approval ratings. You guys hear about stuff like that all the time. Does anybody really care? I mean, do you really care about somebody's approval rating? No. It doesn't mean anything to you. What you care about, though, is if people are running for election or there's propositions that are really controversial out there, you want to know, is that person going to be elected or is that proposition going to pass? That one might make a lot more sense to you because now that may have an impact on you. So the opinion poll, when they're saying, okay, this percentage of San Diegans right now feel this way, this is likely to happen. It is correct. They did it correctly, even if they didn't ask you because they probably took a really large sample, but they have to do the sample really fast because they need to get the results out there before the election comes. Now, I'll give you an idea. You have this great idea, and maybe it's propositions always probably started off as great ideas, but then they get muddled and people add things onto them all over the place. And by the time the election happens, there's so many things, and all of them have good things, all of them have bad things, and it's kind of like the advertising. Which one did they convince you? But you have this great idea, or you think it's a great idea, and maybe this idea will. Let's say you want to do desalination of the water supply in San Diego so we don't ever run out of water. Do you guys know what that means? That's when you take the ocean water and you remove all the salt and stuff. We have an ocean right here. Why do we have a water shortage? Because desalination is really expensive. But what if you figured out a way to, we could do this at not a ridiculous cost. It'll cost all of you guys additional taxes for a few years, to pay for all of the plants that are going on, to the desalination plants. But in a few years, it'll be paid for, and we'll have an endless water supply, literally. You say, this is a really good thing. So you just put it on the ballot? No. You actually do opinion polls around San Diego County just to see if it'll fly. Before you start spending a lot of money doing this, you kind of want to know, will the voters actually approve of this? Does that make sense? By the way, this happens every election. I've been asked so many times for my opinion about something that hasn't happened yet. And if they get enough opinions that are negative, they'll say, you know what, might be a great idea, but San Diegans aren't going to vote for it. This building was built with the Prop N and Prop S funds about 20 years ago. Actually, it was a little more than 20 years ago. The district started floating the idea of getting literally hundreds of millions of dollars to upgrade this campus. Mesa College had the reputation of being the top community college in the United States with arguably one of the worst campuses in the United States. I taught classes in Quonset huts before. You guys know what a Quonset hut is? Those are those metal barracks from World War II. We had several of them on campus, and they weren't really comfortable. Has anybody ever been in the gym at Mesa College? Actually physically walk into our basketball gym? You should. You've been in there? Have you ever seen the movie Hoosiers? The 1950s, the basketball team that wins the state championship. It's based on a true story. I swear, it's the gym from Hoosiers. In other words, that gym looks like it was built in the 50s, and I'm not joking. It is so old and archaic, and there's no AC, and when we have our pre-semester meetings in there, it is so uncomfortable because it is so hot. And it is, for colleges in the United States, I doubt you could find a college with a more rinky-dink, old, dilapidated gym than ours. But our football field is one of the nicest ones in the state of California because that was completely redone. The Prop N and Prop S funds built this building and all the new buildings on campus, all of the stuff you're seeing going on constantly. It was a 10, 15-year project. But before all these things were built, they had to know if San Diegans would approve this because it meant an increase in taxes and things. It's a bond measure. So it has to get paid for somehow. So they would ask people around the county, would you approve something like this? Would you be voting for this? And if most people said no, it never would have happened. But most people did say yes, and it took a really long time. I think I told you guys this first day. I get a call, and it ended up being about a 45-minute interview, and I was asked 100 questions easily. And at the end of the interview, they said, do you or anybody in your family work for the district? I said, yes, I do. Oh, I'm sorry, then we can't count your opinion. And I said, I was really angry. I said, you probably should have let off with that one. 45 minutes of asking me, and I was absolutely for all this because I wanted to see the best campus or the best college on planet Earth become a actually nice campus as well. We have all of this. You don't have any idea what it was like before we moved into this building, how old and rinky-dink all of our buildings were. Most of them have been demolished. But what happened is there had to be polls, opinion polls around the county just to see if people would be interested. So you got this great idea about, the water supply. But before it can fly, we got to find out if people are actually willing to take the tax hike and all these things. More often than not, no. About 25 years ago, there was by the way, the tuition at Mesa College, it's $46 a unit. That sounds outrageous. In 1990, there was only one state in the United States, New Mexico, that had under $100 a unit for community college. Mesa's was $11 a unit. By the mid-2000s, it was $13 a unit. 10 years ago, it was $26 a unit. Then it went up to 36, then it went up to 46. The reason is your education is essentially free here. You're not paying for your classes. The state of California is paying. That money goes into the state's general fund, like the DMV. It just goes in the fund, and then they distribute it. Mesa gets several $1,000s for you being here from the state. But our tuition was microscopic. It was $13 a unit after the year 2000. I had students who came from New York and said, well, our tuition, our community college was over $200 a unit, which was kind of more of a universal norm. We had it so cheap for so long. So there was a proposal, pre-pandemic. Was anybody on campus pre-pandemic? Anybody here? Parking? Do you remember how awful parking has been? Right now it's not terrible because there's not so many students and a lot of online. Pre-pandemic, there's no student on campus that didn't complain about parking. There's just not enough. 30,000 students, but there's not parking for even 5,000 students. So you're parking on the neighborhoods. You got here on time, there was no parking, you drove around. Can't tell you how many times I've gotten emails from students saying, I'm driving around the parking lot, I may not make it to class today for an 8 o'clock class. They're literally spent the entire class driving around looking for a parking space. They floated an idea of building a huge parking structure, and it would increase the student fees. It was like a few dollars a unit, and that was how we were going to pay for it. And they did a poll of the students. The students overwhelmingly rejected it. And I asked my students, I said, why is everybody so against this? I said, well, I don't want to pay any more money for this. I said, but you guys all complain about parking. You know what they said? Yeah, but we won't be around when it's built. I said, oh, that's a great attitude. So it's like, why save the planet right now? You know, because, you know, why should we do all these things for the next generation? I'm not going to be here. It really does not a very good attitude in general, is it? So it got nixed. It never happened. And what people didn't realize, they were paying $13 a unit at the time. They were talking about upping it $2 or $3 a unit. When there was only one other state in the United States that was under $100 a unit. If they upped it $50 a unit, we still would have been the cheapest by a lot. They were talking $2 or $3 a unit, and people said, no, it's too much. But the increases happened anyway because the governors decided, hey, if we add $10, well, actually it's the district. The governor, when Schwarzenegger was governor, he did the first $10, and then the district did the next $10. So the 36 to 46, that $10 does go back to the district. They don't have to wait for the state because there's a lot of things that it's all good stuff. They're not, no one's stealing your money. If you go over to San Diego State and you want to take a class, you just want to take a class at State through Open University. I think it's at least $300 a unit. And by the way, that's really cheap. You want to go to USD and take a class, it's a couple $1,000s a unit. Yeah, so Mesa being cheap is a good thing. You know, we're all happy with that. And then they have the new thing called the Promise Program. My youngest kids are on that. You know what that is? Free tuition. That's the state of, that's everybody, community college. I love that. I think that's just awesome. Okay, so big picture. We know how to do an individual. Individual's easy. There's no question I could ask where you should struggle with an individual probability. But now we're asking for an entire group average. You do everything exactly the same, but you must divide the standard deviation by the square root of n, which means from a calculator standpoint, some of us may struggle. My strongest suggestion is go parentheses divided by parentheses. There's no way you can get it wrong. Parentheses, then your calculator knows that's the whole numerator, divided by parentheses, this divided by this, close parentheses, then your calculator knows that's the whole denominator. Okay? Because otherwise, you do everything right, you write everything down, but then you get a wrong answer because the calculation went wonky. And you're not supposed to do that in your head. You got a cheap calculator. That's it. So this will be the segue now to how we're going to be answering questions as we go on. Okay? We're going to be starting hypothesis testing soon. Hypothesis testing is really the big point of statistics. It's, you've just come out with this great idea, but you've got to prove it's better than somebody else's great idea. Or this wonder drug, we need to know if it's safe for approval. We actually have to do certain things. And all of this stuff is involved in the decision-making process. And so you guys will understand how decisions are often made based on the numbers that we're going to calculate. But the level of calculation is not complicated, not at all. Okay? All right, so let's go ahead and take a break.